So in the lectures until now, we dealt with the construction of these nice geometric spaces X given by affine varieties. We saw they're contained in the ambient affine space. We defined them as sets, and then we started manipulating how can you describe them via ideals. The next big step that we're going to start today is looking not just at the spaces X itself, but looking at functions on these spaces. And this idea that to really understand the space, you need to understand what are the functions on it. This is one of the key ideas of Grothendieck. So you see here, Alexander Grothendieck. So he was one of the big algebraic geometers. He basically revolutionized the field. And this idea that you need to understand functions on your spaces, that is basically one of the key ingredients in understanding how you revolutionize this field. And just as a comparison, I wanted to point out in other subjects of mathematics, this strategy is also very important. So for example, if your geometric object is a vector space, then the function on it are these linear forms, and they form the dual space. And that's an important concept in linear algebra. Similarly, when you have a topological space, and you can start studying the space of continuous functions on it, maybe you can place some nice extra structures on this set of functions, and then often this helps you understand S better. And then finally, when you talk about groups, then there's the characters G star. Which could be, like if you work over the complex numbers, it would be group homomorphisms to C star. And in group theory, those are pretty important concepts if you have seen this before. So in all different areas of mathematics, understanding functions on your spaces is crucial. And so now we follow this proud tradition and ask, like, given an affine variety, what should the functions be? And I mean, as always, we try to stay within the realm where we can use the techniques from commutative algebra. So we don't just allow arbitrary like set theoretic functions, but they should have something to do with the underlying commutative algebras floating around. And the correct definition here is that when X is an affine variety, and a function on X should be described by a polynomial in these ambient coordinates. So you say a polynomial function on X is a map from X to our base field. That's the natural place where functions should take values. So it sends each X to some element in this base field. And this function here should be described by some polynomial in these ambient n coordinates. And then we let A of X, just the set of all such functions, and we call it the coordinate ring of X. And the first basic thing that we should convince ourselves of is that indeed it deserves to be called a coordinate ring. Namely, it is a ring, not only a ring, but in fact, it is a K algebra over this field. And with respect to pointwise addition and multiplication, I mean, given two functions on X, of course, you can always add them by adding them pointwise and multiply them. And to see that this is well defined, you just observe that if F and G are given by some polynomials, which I guess we denote by the same letters, then their sum and their product is still given by polynomial by just taking the sum of the product of these polynomials. So here we basically just use that the original ring here is closed under addition and multiplication. And then we also claimed here it's a K algebra. So you can say this, for example, by saying that there's a ring homomorphism from K into this algebra. And there's a pretty obvious one. Namely, if you have lambda in k, just send it to the constant function f of x is equal to lambda. So in particular, I mean, it's useful to keep in mind the constant function is always an option. It's always a polynomial function here. Okay. So this is a nice algebra, and let's see a first example where we can basically work out by hand what happens. So let's take X to be just a finite set inside A1. We saw these are subvarieties of A1. In fact, these are all the subvarieties except for the full A1. And then we can ask what is the ring of functions on there? What is the coordinate ring? So here's the picture. So somehow you have A1 up to AR. This is the X coordinate. And then you ask, like, on this finite set, what are the functions which are allowed? And here the claim is that if you give me any R values in K, then you can always find a polynomial depending on these values in this coordinate X, such that the value of this polynomial at AI is equal to the BI, the I number that you gave me. And that's just the observation that, I mean, or AI, you have A1, you have some value B1, which you need to reach. Over A2, you have some value B2, and so on. So this gives these kind of blue points. And then it's just classical statement of, for example, Lagrange interpolation, that you can find a polynomial which goes through all these points. But this means there's basically no restrictions. Any set theoretic function from this finite set to K can be a polynomial function. And so the full coordinate ring in this case is just K to the R. You have the freedom of specifying the R values at these points. And I mean, it's a bit strange because normally when we look at K to the R, we see it as a vector space, dimension R over K, and of course it is. But here we see it as a K algebra by the component-wise addition and multiplication. So it's a bit of a weird algebra, but it's perfectly allowed in this context. So this was a very simple example. And here you see we could kind of work out by hand what happens. But if X is a more complicated affine variety in some bigger space, we now want to understand what are the polynomial functions on it. And luckily, we now have all the ingredients to do it, because essentially we will again use this Nullstellensatz. And the statement is as follows. So if X, the affine variety, is given as the vanishing locus of some ideal J, then, well, the map from all polynomials into AX, which sends polynomial f to this function, x maps to f of x, this map is a surjection, and its kernel, the proposition claims, is exactly the ideal of x, which we now can compute with the Nullstellensatz, which is just the radical of J. In particular, AX is the quotient of this by the ideal of X. So it's a very simple form, and we see immediately A of X just depends on the ideal of X. And for the proof, I mean, it's not so big with what we know now. So first of all, these were the functions which are given by some polynomial in n variables. And so by definition, this map here is surjective. Anything here comes from some polynomial. So we get surjection. And then we can just determine what is the kernel by saying, well, f is in the kernel if and only if it is sent to the 0 function on x. So in other words, f of x is 0 for all x in x. But this is our definition of f being in the ideal of x. And by the Nullstellensatz, this is the radical of its defining ideal J. And so this part was pretty easy. And then this isomorphism here follows from the isomorphism theorem. And I think this is the second isomorphism theorem usually, which says that if you have a ring morphism, then the image of this morphism, since this is surjective, the image is everything, is isomorphic to the domain modulo the kernel. And so we can see this. And so this was a bit abstract, and I wanted to have an example, actually two examples here. So both are in A2, and both are described by a single polynomial. So if x is the vanishing locus of this polynomial, y minus x to the 3 plus x, then, I mean, this is a nice kind of cubic, the graph of a cubic function here. And then we see the proposition tells us, well, a of x is the polynomial ring modulo, well, modulo the radical of this ideal, but in fact, you can easily check that this is a prime ideal, so the radical is itself. And then, I mean, if you take this quotient here, then you can basically see this ideal here allows you to always replace y by a polynomial in x. And so in fact, this here is isomorphic to k of x in the variable x. And that's kind of plausible because, I mean, if you want to specify a function on this red part given by a polynomial, then this thing is just telling you, in fact, you only need the x coordinate to specify your value. So if you give any polynomial in x, then in fact, this can describe any polynomial function here, and it describes it uniquely. And another way to see this is to just, I mean, if you're given any polynomial in x and y, then on this locus where y is equal to x to the 3 minus x, you can always replace any term y by that polynomial in x, and you end up with a function which is only described in terms of x. So so that was not so hard. This example is a bit more interesting. So here, v of x and x times y, this is the union of the two coordinate axes, essentially. So it is kind of a union of two simpler things, something that we're going to look at more carefully in a bit. But still, we can ask, like, what is its coordinate ring? And again, I mean, somehow the theorem tells you it's k x comma y modulo the radical of x times y. And well, you can, I guess, just check by hand that, I mean, somehow if a function satisfies that some power is divisible by x times y, then also the original function must be divisible by x times y. So the radical doesn't change anything. And here I wanted to point out that, well, I mean, our job is basically done. I mean, this is a relatively simple description of this ring. But then you can ask, like, can I understand a bit better what this ring does? And so here, I mean, k of x comma y as a vector space over k is just spanned by all monomials. So any polynomial is just a finite linear combination of monomials. And this ideal here, well, this contains all monomials where both x and y appear at least with power 1. So what is left after taking the quotient is those polynomials where either x or y do not appear. And so, of course, 1 satisfies this, and then any polynomial just in x satisfies it, and also any polynomial just in y, and these are everyone. And this has a kind of nice interpretation because you can see this as saying, well, you have 1 degree of freedom for x, 1 degree of freedom for y, and then, well, you can decide what the constant term is. In an alternative way, which you can think about as an exercise if you want, is that this as a vector space is also described by pairs of functions f of x in the variable x and g of y in the variable y. And they need to satisfy, so somehow they're both polynomials, and they need to satisfy that at the origin they agree, which essentially means that their constant term must agree. And then it's basically, I mean, easy to write down a bijection. In fact, you can also see this set here also has a kind of coordinate-wise multiplication. So it actually becomes ring, and you can convince yourself that these rings are isomorphic. And then interpreting this, this is saying these are functions on v of y and v of x that agree at the origin. And that's a kind of nice interpretation because it says that, I mean, on this union of here of affine varieties, of these simpler affine varieties, a function is just a function on one, a function on the other, and they agree on the overlap. Now, I should warn you, this is not always the case. This uses something nice about this union of varieties, but at least in this case, it nicely illustrates that this proposition here really computes this coordinate ring very nicely. Okay, so these were the examples, and as also kind of nice example of the ring of this proposition is that the ring of all polynomial functions on the entire space AN is just a ring of polynomials. And to see this, well, I mean, AN is the vanishing locus of 0, because 0 vanishes everywhere. You can take the 0 ideal here. And so the ideal of AN, if you, I mean, you can in this case, if you like, throw the whole Nullstellensatz at it, is the radical of the 0 ideal. But I mean, the 0 ideal in this domain is a prime ideal. And so its radical is itself. And so this doesn't change anything. And so the ring of the coordinate ring or the ring of polynomial functions on AN is just k of x1 up to xn modulo the 0 ideal. Modulo 0 doesn't change anything. So this proves the corollary. So this was the kind of technical way to see the proof. But then the slogan, if you look at this, is just saying that a polynomial in the n variables is determined uniquely by its values at all the points in AN. So, so this means not just, I mean, by definition, the polynomial function is determined by its values, but in fact, for AN, you can uniquely reconstruct the original polynomial. And that's often a nice thing to keep in mind. Note here, as a word of caution, again, this depends very much on the fact that we worked over an algebraically closed field. So for example, if we worked over the field F2 with 2 elements, then you have a polynomial f of x equals x squared plus x, and its values at the 2 points 0 bar and 1 bar, well, if you plug in 0, then you get 0 squared plus 0 is 0. If you plug in 1, you get 1 squared plus 1. So 1 plus 1 is equal to 2. But 2 is 0 in our field, so you also get 0. But, so this means that this polynomial here gives you, as a polynomial function on A1, gives you 0 at all points, but it is not a 0 polynomial. So, so this shows that this corollary is just false for k equals to F2. And we really did need, at some point, this kind of Nullstellensatz. Okay, and so this, for now, was the definition of the coordinate ring of an affine variety. And then next time we're going to see how to use this to define inside the variety things called subvarieties, described by polynomial equations now in this coordinate ring.